So a number of years ago, LA Fitness opened up a facility down here in Royal Oak, right at the end of Washington, and to kind of get people to sign up, they had a couple different offers. For a couple to sign up, you could spend, let's see, $250 a month plus 55 a month, or $250 sign up plus 55 a month, and that would be your payment. Another possibility, another thing that they offered was you could spend $350 in a sign-up fee and then spend $45 per month. So the question is, as a consumer, which one would you buy? Which sign-up should you go for? Planet Fitness. Planet Fitness is opening up a new one on 696 in Coolidge. But if you're choosing amongst these two, which one would be better? $350? The answer is it actually depends on how long you're going to be a member. If you're going to be a member for a short time, then you want to go for the cheaper one in terms of sign-up fee. But in the long term, you're better off here. So a good question to ask is, well, where's the break-even point? And that's really my motivation in showing you this example. The break-even point is where these two lines meet. And that's what we're going to work on in section 12.1, is trying to find where two lines intersect each other. Now in this case, and we can do the math later, it works out that after 10 months, that's the break-even point. So after 10 months, you're spending $800 with either plan. After that, the plan with the lower slope is going to be better. Higher slope, well, price there is just going to continue to be much, much greater than what you're paying this way. So there's some vocabulary that surrounds these types of problems. They're called systems of equations. Systems of equations. And basically what you're doing is you're trying to find that point, the one that I have highlighted here in green, where two lines intersect each other. Now there's several possibilities, different things that can happen when you're trying to find that point. And we have some vocabulary that describes that. If you find this point, a point where two lines cross each other, then that's a solution. And if you have at least one solution, then your system of equations is consistent. So this is a consistent system of equations. Some more vocabulary. If instead of having two different lines, if your two lines are the same, that is one right on top of the other, then you have a dependent system of equations. Well, if you're not dependent, what are you? Independent. Since these two lines are different, this is an independent system. So we're looking for that point because that point is supposed to satisfy both equations simultaneously. Hence the name, a simultaneous system of equations. Let's take a look at problem number 16 in the book. Try and decide if the solution that they give there, or if the point they give there, is a solution to the system of equations. So this is section 12.1. Number 16, they give us this point, -3/4 and 2/3. We want to know, does that solve this system? So 4x plus 3y equals -1, and 4x minus 3y equals -5. Is that a solution? Well, there's a couple ways we can do this. You could graph this system of equations and try and see, do those two lines cross each other at that point? And that would work. But what's another way I can see if this is a solution to both of these equations? Perfect. So what they're really giving you is x and y for both of these equations, or to plug into both of these equations. And we want to see, does 4 times negative 3/4 plus 3 times 2/3, does that equal negative 1? And at the same time, it also has to satisfy this equation. 4 times negative 3/4 minus 3 times 2/3 has to equal negative 5. Okay, well, let's take a look here. 4 times negative 3/4. The 4's will cancel, leaves me with negative 3. Here the 3's cancel, leaves me with a 2. Negative 3 plus 2, yeah, that's negative 1. So that one works. How about the other one? Success there. 4 times negative 4, again we get some nice cancellation. So that gives me negative 3 minus what? Minus 2, good. So minus 2. Does that equal negative 5? Yes, it does. So it satisfies both equations. So the answer to the equation, or the answer is yes. This is a solution. And that makes this a consistent system of equations. It's also independent because these are two different lines. They're not the same lines. So it's consistent and independent. Now there's a lot of different ways you can try and solve a system of equations. One of them is simply by graphing. And let's see if we can't take advantage of a graphing approach for the following system of equations. Y equals x and y equals negative 3/2 x. Keep in mind what we're looking for. We're looking for where two lines cross each other. And since we're getting close enough to the end of the semester, it's not a bad time to do a little bit of review here. One of the things that I want you to know come time for the final exam is this: y equals mx plus b. Who remembers what that's all about? Gil? Slope-intercept. Slope-intercept form. Good. So let's list the slope and the intercept on these two. What's the slope of the first one? It's always going to be the coefficient. It's going to be the number part. So it's going to be a 1. How about the y-intercept? Zero. It's not really written, but it's kind of understood. There's a 0 here. So b and 0. How about over here for the second one? All right, so for the second one, m equals negative 3/2. What about the slope, or excuse me, the y-intercept in the second one? All right, so I'm getting hand signals thrown in from the sidelines, and he's right. 0. Now I could graph these to try and find where these two lines intersect, but I kind of jokingly refer to this as solving by graphing without graphing. Do I really need to graph this to see where these two lines intersect? Where do they meet? They meet at the origin. Here's your graph right here. So we can tell because these two lines have the same same y-intercept that they cross at 0, 0. There's your solution. By the way, which graph is which? Which graph is this one? Has to be y equals x, right? Because it has a positive slope. As you move from left to right, it's increasing. And the other one, by process of elimination, y equals negative 3/2. But again, you should see that as you move from left to right, the line is decreasing. Columns, is this consistent or inconsistent? Why? Yeah, that one spot where they meet is your solution. That point, 0, 0, solves both equations. If you plug it in, 0 equals 0. That's true. 0 times negative 3/2 equals 0. So this point is a solution to both equations simultaneously. So yeah, it's consistent. Because these are different lines, it's also independent. So consistent, dependent, inconsistent, dependent, etc., etc., etc. Because the two lines are different. It's not one line right on top of another. Let's move down to the next example. And I don't have the equations for this, and I'm not sure we really need the equations for this. Is there a solution to this system of equations? No. The two lines are parallel. I could actually come up with the equations, but it doesn't really matter. So, is this consistent here? Lauren, if you're not consistent, what would you be? Inconsistent. Thank you. So it's inconsistent. Are these two lines different? Yeah. So it's inconsistent, independent. So that's another thing that can happen. So we've seen two different things that can happen so far. When you're graphing a 2x2 system of equations, the two lines can cross each other. They can be parallel to each other. Let's take a look at this last one, which is really your problem number 24 from the book. Now, I've already graphed this one here. And as a reminder, one way to graph these things is by setting x and y equal to 0. So if I set x equal to 0, then I could solve for y. Y would be 3. If I set y equals 0, I get x is 6/5, which is 1.2. But I'd like you to do the same thing for this one. Make yourself a little t-table, set x equals 0, set y equals 0, and plot some points, and then graph the other line here. See what you come up with. Just going to do a little sound check here. There we go. What are you finding when you go for 2 more points? You should be getting the same points. If you set x equals 0, you get negative 4y equals negative 12. Divide both sides by negative 4, you get 3. Set y equals 0, negative 12 divided by negative 10, gives you 1.2 or 6/5. So when I plot those 2 points, what happens? You get the same line. So really, there's an infinite number of solutions here, because these 2 lines are one right on top of another. So, wow, that's kind of crazy. But does this mean a system of equations like this is consistent or inconsistent? What would you say about this one? Consistent. Yeah, there's at least one solution. In fact, there's an uncountably infinite number of solutions. So, consistent, and here you go. This is where you finally get to use dependent, is when you have one line right on top of another. That's the only place that you have a dependent system of equations. Okay. Beautiful. So we did a lot of work solving these equations by graphing. And the reason I like to start out such systems equations like this is because we're going to move on from graphing to a lot of other things. But it's very easy to lose sight of the fact that what you're really trying to find underlying all this is a simple point, where those 2 lines cross each other. It's not uncommon for me on an exam to give a nasty set of equations, involving fractions, etc. And then I'll say, use the graph to help solve the system of equations. And the equations are going to be like 1/4 x plus 3/4 y equals 1, and 5/4 x minus 1/4 y equals 1, or something ugly. And then I'll ask you to solve the system of equations. What's the solution to a system of equations like that? You're thinking too hard. 1 and 1. That's it. And that's the point of a problem like that, is that I want you to know that what you're looking for is this point. We can find it in a lot of different ways. And the rest of our lecture in this section, we're going to spend trying to solve the system of equations without the graph. Okay, we're not going to worry about graphing that. It's not a real good way to solve things. Mostly because a lot of times our solutions aren't going to be nice integer numbers. But don't lose track of the fact of what we're trying to find. Now, solving that's going to take 2 different forms. One of them is going to be a method of substitution. The other one's going to be an addition method, or sometimes called elimination. Elimination sounds cruel, so we'll try it. We'll just call it substitution. But whatever you want to call it, let's start out with a problem like number 36. So we're going to start with some examples of substitution. And I'm hoping this looks familiar from a previous class. In problem 36, we're given y equals x plus 2 and x plus 2y equals 16. If I'm going to solve this by substitution, it really doesn't get much better than this. You've already got y equals something. In this case, y equals x plus 2. What if I wanted to use that and I'm going to replace y in the other equation by that x plus 2? So this is going to become x plus 2 times x plus 2 equals 16. What's the advantage in that? What did I gain by doing that little bit of hocus pocus? Yeah, I got rid of the y, right? This equation just depends on one variable, which is x, and we can solve that. So x plus 2x plus 4 equals 16. 3x plus 4 equals 16. This is just a linear equation. Subtract 4 from both sides, 3x equals 12. So x equals 4. Yay! Now keep in mind that this is just part of your solution. Why is it just part of your solution? Yeah, we need to figure out what y is. So yeah, you have to take the x, plug it back into one of these equations to solve for y. Which equation would you choose? Yeah, the first one, hands down. Y equals x plus 2, so y equals 4 plus 2, meaning y equals 6. So, yay. Y equals 6 here. What you'll see written in the book or on WebAssign, if you look up your solution there, is not going to be x equals 4, y equals 6, but 4 comma 6. It's going to be written as an ordered pair. Now, if you want to write it like that, that's great. I'm happy enough if you just give me x equals something and y equals something, but please give me both. If you don't give me both, you're going to lose at least a point. How are we doing on that first one by substitution? Let me ask Mackenzie. Let me graph these things. Do you think I'm going to see two lines that cross each other? And if so, where? Yeah, these two lines should cross each other at 4, 6. So y equals x plus 2. Man, plus 2. And the other one was x plus 2y equals 16. Bingo. 4, 6. So nice. It's exactly what we would have expected. Two lines across each other. Okay. Is this system of equations consistent or inconsistent? Consistent. Dependent or independent? Consistent and independent. The lines are different, so it's consistent, independent. Consistent, independent. Well, there's probably going to be one question where I ask you to just, to show me that you understand the difference between consistent and inconsistent, dependent and independent. So this is vocabulary that I want you to know, but no, I'm not going to ask you to write that in every question. No, most of it it's just going to be solved if you can. So, all right, let's try another one. Problem number 40. (2x minus y equals negative 21) and 4x plus 5y equals 7. This one's not quite as tailor-made to set up or to do by substitution as our last one. It's not bad, but it's not perfect either. If I'm going to do this by substitution, typically what I look for is a variable in my system equations that has a coefficient of 1 or negative 1. It's easiest to work with. And we can see in the numerator, or the first equation, that this has a coefficient of negative 1. So let me solve for y from this first equation. You can do that in a couple ways. 2x minus y equals negative 21. You could subtract 2x from both sides and get negative y equals negative 2x minus 21, and then divide by negative 1 everywhere and get y equals 2x plus 21. And that's fine. I'd take a different route. If this were me solving it for myself, I'd say, you know what? I want to make that y a positive y. So I'll move it to the other side to try and get it by itself. And once I do that, I want to get rid of the 21. So I'll move it to the other side. When a term changes sides, what else changes? The signs. Change sides, change signs. So this quickly gives you 2x plus 21 equals y. Either way, you've got an expression for y. So let's take that expression for y and plug it into the other equation. Make sure you don't substitute back into the same equation. So it's going to be 4x plus 5 times 2x plus 21 equals 7. Okay, well, that's going to be 4x plus 10x plus 105 equals 7. Combine like terms. 14x plus 105 equals 7. 14x equals negative 98. That is, subtract 105 from both sides. What's our last step here? Divide both sides by 14, so x equals negative 7. Nice. If x equals negative 7, you've got 3 choices as to where you want to plug back in and find y. So let me call them A, B, and C. Yeah. That's what was actually the purpose of that question. I want you to think about it, but yeah, absolutely, go with C. Well, you've already got y solved for here, right? So go with C. Y equals 2 times negative 7 plus 21. And we get y equals 7. Overall, negative 7 and 7. Abdulaziz, is this system of equations consistent or inconsistent? Yeah, consistent. I found a solution, right? Consistent. Dependent or independent? Independent. Yeah, independent because the lines are just 2 different lines. If you were to graph this, you would see them cross each other at this point, negative 7 and 7. Okay. Let's try a couple more. Do you want another one by substitution, or are you okay with substitution? We're okay? All right. Let's try the addition method then. Let's take a look at problem number 46. This is the addition method. Sometimes it's called elimination. In problem 46, the 2 equations are x plus 2y equals negative 21 and x minus 2y equals 11. The addition method is pretty nice. A lot of times I just use the addition method. The nice thing about this method is that it lives up to its name. We're going to add the 2 equations together. When I add these 2 equations together, Bailey, what would I get? These will cancel out, yeah, so that's nice. X plus x is 2x. Negative 11 plus, excuse me, negative 21 plus 11 is negative 10. Wow. Wait a minute.
That was easy.
X equals negative 5, right? Nice. We're not quite done, though. What else do we have to do? Okay, we got to find y. So pick whichever of these equations you think looks friendliest, plug it back in and find y. does it? It does sound a little high-pitched today. You know what? I screwed this up, didn't I? I need to plug this back in for x. So let's pick up the first one. Negative 5 plus 2 times y equals negative 21. Add 5 to both sides. 2y equals negative 16. So what does y equal? Negative 8. So negative 5, negative 8 is your solution to the system of equations. Nice. So there's the addition method. This one worked out pretty nice. Could we have done this one by substitution? Sure. Just take the second equation, move the 2y to the other side. You get x equals 11 plus 2y. Substitute that into the top equation. You'll be all set to solve very easily. Now, where the addition method gets a little bit more challenging is if things don't line up quite as nice. So, for instance, let's see here. Let's take a look at problem number 42. 3x plus 5y equals 4, and 5x plus y equals 14. If I add these two equations together, am I going to get anything to cancel out? So what you can do is you can multiply one equation or the other or both by a number so that you can try and make these things cancel out. Yes, let's look back at problem 46. The reason we got some nice cancellation was because of these two numbers. You had 2y and negative 2y. Same number, opposite signs. So an easy way to get that down here would be to multiply the bottom equation by what? Negative 5. So multiply by negative 5. And let's see what new equation that gives me. Now, I didn't change the top equation. That's still 3x plus 5y equals 4. The bottom equation is now negative 25x minus 5y equals, that's what, negative 70? When I add these two together, I get negative 22x equals negative 66. Well, isn't that special? It works out even. What does x equal? X is 3. Now, if x is 3, you can plug into either of these two equations and solve for y. I'm thinking the second equation looks easier. You can go with the first one. It really doesn't matter. 5 times 3 plus y equals 14. If I subtract 15 from both sides, I get y equals negative 1. So 3, negative 1. Yeah. Good question. What if I would have chosen the first one? Well, then I'd end up with 3 times 3 plus 5y equals 4. So that's 9 here. I'll subtract 9 from both sides. I end up with 5y equals negative 5. And when I divide both sides by 5, I end up with negative 1. Okay. On 46. So here, well, originally I substituted in, accidentally I substituted in for y. I should have substituted in for x. So I fixed my mistake, went back and I said, okay, well, let's substitute in x is negative 5. I did that in the first equation, and then I solved for y from there. Okay. But what you should do is try and pick whichever equation you think looks easiest. So in my mind, I thought, gee, if I had y all by itself, the second equation looks easiest. I mean, the first equation wasn't that much harder. So either way, you end up with the same solution. 3, negative 1. Norman, I'm going to graph these two equations. I want you to make a prediction. So 3x plus 5y equals 4. Are these lines going to cross each other? And if so, where? Yeah, they should cross each other at 3, -1. So here's the first equation. Here's the second equation, 5x plus y equals 14. Equals 14. How about 14? Perfect. 3, -1. Is this system of equations consistent or inconsistent? Consistent and independent. Nice. Let's go back and do another one by substitution. So that one's going to be problem number 52. Get those equations up for you in just a second. 8x minus 4y equals 16. 2x minus 4 equals y. So again, another one that's tailor-made for substitution. Perhaps, out of fairness, I should warn you that this one's a little bit unusual. It's not like maybe for the problem. Messing with me. They do. You don't get an x. Well, let's take a look at this one then. So if I substitute in here, it would be 2x minus 4. And I'll distribute the -4, so 8x minus 8x plus 16 equals 16. And I hope that you notice that the left-hand side has some cancellation, right? Those disappear. So we're left with 16 equals 16. There's no x, you're right. X is gone. But is this true? Does 16 equal 16? Yeah. So I even saw a few people subtract 16 minus 16 and get 0 equals 0, which is awesome because it always gives me a chance for some Letty. Yay. 0 does equal 0. So what's going on with that one? What do you suppose I'm going to see when I graph this? They're the same line. Now this is something that's important here. Let's see. So we're going to graph 8x minus 4y equals 16. And then graph 2x minus 4 equals y. And you're getting the exact same line. Now to see that in a different way, let's play around with our equations. if I were to take and swap these two, so put the constant on the right-hand side and this on the y on the left-hand side, can anyone tell me what equation that would rearrange to? If I move the y over here and the 4 to the right-hand side. Good. 2x minus y equals 4. So that's just rearranging the second equation. But can you see a relationship now between these two equations? Exactly. If you multiply this one by 4, you get this one. So that's why we're seeing this kind of a strange thing happen, is that we ended up with the variables canceling each other out. That's because this is really the same equation. There's an infinite number of solutions here. But what I want you to realize is that if that's true, if you have a dependent situation here, that, yeah, the variables are going to cancel out, and you're going to get something which is true. And that's the big thing here to realize, is that even though this is a silly statement, 16 equals 16, it is true. 16 does equal 16. Yeah, it looks silly, but it's true. Let's take a look at problem number 54. 4x plus 8y equals 15. And x equals 2 minus y. I kind of find this one odd. I really have no explanation as to why the author didn't distribute the 2. Other than maybe he just wants to make you work a little bit harder. Okay. So if I distribute it, I can think of my two equations this way. 4x plus 8y equals 15, and x equals 4 minus 2y. Which way would you solve this one? Would you solve it by the addition method or the substitution method? I use substitution, yeah, all day. Look, you already got a nice expression for x. Plug it in over here. 4 times 4 minus 2y plus 8y equals 15. Why don't you work on that while I pull up their graphs? Shh, shh, shh. Don't spoil the surprise. Spoiler alert. Well, that's why you want to think about the geometry of what's going on with these types of problems. So 4x doesn't mean you're divorced from any other branch of math. 8y equals 15, and x equals 2 times 2 minus y. So what happened when you tried solving here? 16 minus 8y plus 8y equals 15. And like the last one, you should see that two variables drop out. But unlike the last one, we end up with something like this. 15 is equal to 16. Was I asleep that day in high school when they taught me that? No. 15 doesn't equal 16. So what's up with this one? It's not true. But what's that telling me about my system of equations? There's no solution because they're parallel. They don't cross. So this is an inconsistent, independent system of equations. If you were to graph this, and here's one line, here's the other line. Those two lines are one right on top of each, well, not quite right on top of each other. Let me see if I can zoom in a little bit. They're parallel lines. Kind of tough to see, but they're parallel lines. So there's no solution. You want to keep that in mind as you're working through some of these problems. From time to time, you're going to see stuff that, all right, there's no solution. And what you'll find is something like this happening. 16 equals 15 or 7 equals 5, whatever the case may be. You'll get a statement that's not true. All the variables have canceled out. You get a statement that's not true. That's telling you you've got an inconsistent, independent system of equations. Let's do one last one from this section. Problem number 30. So 3/5 x plus 1/4 y equals negative 11 over 10. This is number 30. And 1/8 x equals 13 over 24 plus 1/3 y. Okay. Can someone put into words for me what you might not like about this problem? Fractions, yeah. The dreaded F word, right? All right, so let's do something about the fractions here. And the something we're going to do is we're going to multiply through by a lowest common denominator to clear out the fractions. So in the case of the first equation, what should I multiply by? Multiply by something a little smaller. I'd go 20. 40 would work, but I'd go 20. And in the denominator, LCD there is 24. So I'll have 20 times 3/5 x plus 20 times 1/4 y equals 20 times negative 11 tenths. You can and should do the cancellation here. The cancellation looks like this. 5 goes into 20 4 times. 4 times 3 is 12. So I'll get 12x. 4 goes into 20 5 times. 5 times 1 times y is 5y. 10 goes into 20 2 times. 2 times negative 11 is negative 22. Why don't you try the second equation? See if you can't simplify that one. Who's got that second equation simplified? Gil? Perfect. 3x equals 13 plus 8y. So again, some nice cancellation. 3 here. The 24 cancels out all together. 3 goes into 24 8 times, so 3x equals 13 plus 8y. So there's our two system equations. A lot more friendly looking version of this because we got rid of the fractions. Let me move the 8y term to the other side and start solving it over here. 12x plus 5y equals negative 22. Lisa, when I move the 8y to left-hand side, what happens to my equation? What's it going to be? Good. 3x minus 8y equals 13. It still doesn't look terribly friendly, does it? But there's a decent way to solve this without working too hard. Now, sometimes you're going to have to multiply both equations by a number. For instance, if I multiply the top equation by 8 and the bottom equation by 5, I'd end up with a 40 here and a negative 40 here, and that would cancel. I don't have to work that hard in this problem, though. What else could I do? Multiply by what and where? Yeah. I'd multiply the bottom equation by negative 4. So that gives me 12x plus 5y equals negative 22. Negative 12x plus 32y equals negative 52. When I combine like terms, I get 37y equals negative 74. And doesn't that work out special? Because y equals negative 2. Whew. Thought this was going to work out ugly, didn't you? Nah, not in this class. So let's take y equals negative 2 and plug it into one of the equations. Any favorites? Second equation? Okay, second equation it is. 3x minus 8 times negative 2 equals 13. So 3x plus 16 equals 13. Subtract 3 from both sides. Excuse me, subtract 16 from both sides and then divide by 3. X is negative 1. Consistent, independent. Bailey? Great question. It's completely up to you. Completely up to you. Sometimes what I'll do is I'll give you two problems side by side and say do one by addition and one by substitution. And even there I'll let you pick which one you want to do. Just show me one of each. But other than that, you're free to solve any way you want. We're going to learn a couple more ways to solve system equations. Actually, probably one more way. But there's tons of ways to solve system equations. An awful lot of them. I wasn't really following the instructions in the book. Yeah. No, I wanted to use that one as a good example of how to get rid of the fractions. All right. But yeah, actually that's a good example of a test question that I could ask. I'd give you a system of equations like that and ask you to use the graph to find the solution. The funny sad thing that I see sometimes is people do an awful lot of work. And they work really, really hard, and they get their solution of negative 1, negative 2. But it was right there all along on the graph. So, yeah, if I give you the graph, use the graph. I mean, that's what it's for. For homework, yes? I'm not going to ask that you solve it by a graphing calculator, but if you give me a second, I will show you what you could do. So, for homework, try problems 11 through 15. You should probably do one of these maybe by graphing. So maybe we'll do 21. 23 through 25. You know what? No, those are more by graphing. So we'll skip that one. Let's do 35 through 53. That's pretty good. You might want to practice one more like 57. But I think you should get enough practice there. I'm hoping that a lot of this stuff looks familiar. Oh yeah, and then as far as solving this on a graphing calculator is concerned, let's take a look at a problem like 32. So now you're not required to know the graphing calculator in this class. I know that more of you have them than my college algebra students, which I find continually amusing. Y equals negative 0.45x plus 5, and y equals 5.55x minus 13.7. So what you would do is plug both of these into your equation editor. So that means you hit the y equals key on your graph. If there's anything there, use the clear button underneath the arrow keys to get rid of that stuff. Type in negative 0.45. Use the negative key on the bottom row of your calculator, not the subtraction key. Negative 0.45x next to the alpha key. Plus 5, that's your first equation. And then 5.55x minus 13.7, that's the second equation. We have to tell our graphing calculator where we want to see the graph. Since I really don't know what to expect, I'm going to take kind of a shotgun approach. That is, I want a wide spread. So if you hit the zoom key, one of the options is zoom standard. So zoom and then press the number 6, and we'll see a nice graph. There we go. So an easy approach is to just hit the trace key and kind of move over close to the solution. So it's close to 3.18 and 3.56. If you want an exact solution, you can do that too. Hit the second key, then the trace key. Does there look like something that's interesting off of this menu? Intersect. So just hit enter like 3 times until it gives you the exact solution. 3.11666 and 3.5975. So that's how you would do it on a graphing calculator. The problem that you would run into for some of these, even like a problem like this, is that you'd have to solve for y before you can put it into your calculator. So in this case, you'd have to have y equals negative 12x minus 22 divided by 5. You'd have to enter that expression. You'd have to do likewise for this one. You know, how much time you want to invest in that is up to you. All right, all set.